Welcome student. Today we will study proof of residue theorem. What residue theorem states that if fz is an analytic function in closed curve C region except at finite number of poles within C, then integral C fz dz is equals to 2 pi I times sum of the residue within C. Going in proof of this particular theorem, there is a region C and inside there are certain points which are pole for function fz. Fz is the function defined over this circular contour C, and singular point of singularities are there z1, z2, z3, number of singularities over there. So to make proof of this particular theorem, first of all we draw this particular region and isolate every singularity from the region by drawing small circles C1, C2, C3 and so on, and make this multiple connected region by making certain number of cross cuts. Now by Cauchy theorem we all know that integral fz dz over C is equals to integral fz dz over C1 plus integral C2 fz dz plus integral C3 fz dz and so on. There are number of terms in the right hand side of this equation as numbers are singularities in this function fz. Now to solve further, we just make a Lorentz series expansion of fz about these points z1, z2, z3 and so on to evaluate the value of different integrals. Now fz, the Lorentz expansion of fz is equals to sigma of an z minus z1 to the power n plus principal part must be there b1 z minus a plus b2 z minus a to the whole square plus b3 z minus a to the whole cube and so on. This part is known as principal part of Lorentz expansion. Now we can integrate above this equation 1 with respect to z. We would get fz dz over c1 is equals to integral c1 is n z minus z1 to the power nc dz plus c1 b1 upon z minus a dz and add up all rest terms to get next integral as bn upon z minus a to the power n dz and addition of all these terms, that is summation, n is equals to 2 to infinity. Now by Cauchy theorem we know that integral c1 an z minus z1 to the power n dz is equals to 0, because for this particular function the function is analytic over there. So by Cauchy theorem this integral is equals to 0. Now last integral sigma bn upon z minus z1, this is z1 and z1 to the power n dz. We try to prove and find out the value of this integral over c1. Let's draw again c1 explicitly. c1 and this is the point z is equals to z1. So by theory we just take z is equals to z1 plus r e to the power I theta, where theta varies between 0 to 2 pi. Means, as we know, the equation of this circle C1 is equals to z minus z1 is equals to r e to the power I theta. So z is equals to this, and dz is equals to r I e to the power I theta, where theta varies from 0 to 2 pi. If we substitute all these values in this integral would become, this is equals to sigma n is equals to 2 to infinity integral bn z minus z1 is equals to r e to the power I theta to the power n times r I e to the power I theta d theta. On simplifying this, we would get this as is equals to sigma of bn upon, as we are integrating with respect to theta, so all other terms are constant over here, r to the power n minus 1, and numerator I is there, into e to the power minus I theta n minus 1 upon n minus 1 times upon thing times d theta over limit 0 to 2 pi. 0 to 2 pi. Now when we integrate this particular integral, this would become sigma bn I upon r to the power n minus 1 integral e to the power minus I theta n minus 1 upon I times n minus 1 over limit 0 to 2 pi, and this is equals to bn upon r to the power n minus 1 within bracket e to the power minus I n minus 1 times 2 pi minus e to the power 0. As we know that e to the power I theta is equals to cos theta plus I sin theta, and when we put this Euler formula in this particular integral, and also we know that cos of 2 pi is equals to 1 and sine of 2 pi is equals to 0. On substituting these values over here, this term would also become 1 and e to the power 0 is also become 1. So this is bn sigma over there r to the power n minus 1 into n minus 1 with this 1 minus 1 is equals to 0. So the third integral, this would also become 0, this is become 0. So leftover term is integral c1 fz dz is equals to integral b1 upon z minus z1 over dz. So by this we can write down this as equals to integral c1 fz dz is equals to 0 plus integral b1 upon z minus z1 times dz. Now by Cauchy integral formula, we know the value of this particular c1 is equals to 2 pi I times f of a, or residue at z1. The value of this is equals to 2 pi I times f of z1. This is for point z1. Similarly, for point z2, point z3, all other integrals would also ci f of z dz, ci f of z dz is equals to 2 pi I. This I are not identical, so we take this I as different. Cj fz dz is equals to 2 pi I f of z j. Residue at f of zj, residue. So by using all this theory, we can write down c fz dz as this was equals to c1 fz dz plus c2 f of z dz plus and so on, and all these values are equals to 2 pi I times residue of f of z1 plus 2 pi I times residue of f of z2 plus and so on. This is equals to 2 pi I times residue of, take summation of all these residue, take bracket, residue of f of z2 plus and so on. This can also be write down as 2 pi I times sigma of residue of f of z. So this theorem is known as residue theorem, and this statement, and this is the process of proof of residue theorem. Hopes you can understand this particular proofs. Thank you.